Thank you for the introduction. I understand that you all are working on trying to get some information from NASA to be able to turn into some lesson plans that you can take back to your classrooms. And so I'm going to talk about advanced manufacturing and the role for modeling and simulation as we see it in advanced manufacturing. I'm going to go fairly quickly through the first part of the presentation because the intention there is really just to give you a sense on what we're doing, why we're doing it, what some of the potential is, because you're teaching the engineers of tomorrow that are going to be using this technology, I hope, in being able to build products that help not only NASA but help the nation. And so I will slow down when we get to the point that I think that we've got some information that may be useful for you to be able to take back into your classrooms immediately. But I hope that you get a feel for the overall picture. We're going to save questions until the end, and so and I'll try to make sure that I keep the pace so that we can so that we leave plenty of time for questions. Just one last thing: the presentation, the videos that I've got in here, as well as another video that I'm not showing from some of my zero-G flight time, is on the wristband that you all got with the presentations and everything. And for those of you that are remote, you will be getting those wristbands at some time. So let me get started. Okay, just a brief outline. I'm going to start with an introduction on the technology we've been developing, which is called Electron Beam Freeform Fabrication, or EBF3. And we've got a lot out there on the web, so if you Google my name or EBF3, you'll find more than you wanted to know. Talk next about process control, residual stress and distortion, certification, and then the influence on future designs, how this may be used in the future. And end with some of the supportability in space. And so it's that space section at the very end. That's the part that I'll slow down a little bit to give you something that may be useful for you to develop into lesson plans for your students. So first, what is EBF3? Electron Beam Freeform Fabrication. This is a rapid metal fabrication process. So it's a layer additive process. We start, and I've lost Karen, so I'm going to start this without her. So we start with a piece of base plate. This is just 1/4-inch aluminum base plate. And then we take wire, and I'll pass these around for you to see it. We take wire. This is a 1-pound, 4-inch diameter spool of wire. Both of these are aluminum, and so what we do is we start with the base plate. We create a molten pool, and then we deposit the wire onto the base plate. The advantage of this is it's a layer additive process, meaning we can build things up layer by layer, and it doesn't require molds or tooling or, it's a lot less expensive. You can go straight from a CAD drawing to building a part. Properties are very equivalent to what we would call rot properties, and so these are the properties that rot properties are if you bought a piece of aluminum today off the shelf, that's in a rot condition. So that's WROUGHT. Yes, rot. And so far we've worked with aluminum, a lot of different alloys that are of interest to aerospace. So we've worked with aluminum alloys, we've worked with titanium, we've worked with stainless steel, and nickel-based alloys. And so, different temperature ranges for different applications on an airplane, but we've worked with a number of different metals that you would find traditionally on airplanes. So some of the benefits, one of the reasons that you want to do this is it allows you to build a component. Sorry. So it allows you to build the component near net shape, which means that instead of starting with a big block of material and machining it down to your final part, you end up just putting the metal where you need it. It's very similar to if you've heard of rapid prototyping, stereolithography. Some of you that may be working with some engineering or groups may have heard of some of those technologies. Very similar. A lot of different technologies are building up in plastic. We're building up in metal. The reason that we want to do this for aerospace parts is you can build a part, instead of building a lot of little parts and having to assemble it, you can build it all in a single piece just by building up the layers and designing it. It allows us to go more efficient on some of our designs. We can reduce the weight of structures by being more intelligent in the way we design the structures. It allows us to improve the performance of things like aircraft or spacecraft or golf clubs. I think that's the place that it's going to be used first. But and as I pointed out earlier, it's a direct art-to-part without molds or tooling. So the so one of the values, and something that we're hearing a lot of in the federal government these days, is advanced manufacturing and green manufacturing. So how can we reduce the waste and reduce the energy input and still end up with a good product? And so one of the things that this process allows us to do is do both. We can reduce the amount of energy that goes into building a final product, and we can reduce the amount of raw material that we're throwing away just by building it differently. So I've pretty much already talked about this. This is, and some of these pictures do not show up very well on the remote locations, but you will have all of these charts for you to be able to reference on your disks. And so, but we start with a CAD drawing, so a computer-aided design drawing. You build that 3D part on the computer, and then we use an electron beam to create a molten pool. Feed wire into that molten pool, and then translate the whole thing, and we build it up layer by layer. And this is a video of how the process works. So you can see the size of the chamber we're working in. We're working in an electron, we're working in a vacuum chamber that's about 7 by 9 by 9 feet. And so it's a big vacuum chamber. We pump it down in 30 to 45 minutes or so. On a hot, humid day like today, it may take closer to an hour. But we pump it down, and part of the reason for working in a vacuum is it gives us a clean environment, and it also prevents the stream of electrons from bouncing off of the molecules in the air and scattering that electron beam. So it allows us to keep a very tightly focused beam. And what you're going to see here is the process running. So we're going to show you the door opening, but normally we load the stuff into the chamber, and we close the door. At this point now, we're pumped down and we're looking through a window. The electron beam is coming from the top straight down, and so all you see of the electron beam is the shiny part where it's actually melting the aluminum in the base. Our first layer we just used to clean off any of the oxides and kind of preheat the plate a little bit so that we've got a good layer to stick to. At this point now, we're feeding wire into that molten pool, and we're translating the whole part to build it up layer by layer. This is aluminum. The wire diameter is about 63 thousandths of an inch in diameter. We're getting a bead width of about 1/4 of an inch across. And so just to give you a feel for some of the components that we've built using this kind of a process. So a lot of what we do is just build straight little walls like this, and we take those, we'll cut them up and use them for characterization, mechanical testing, and microstructural analysis. But we've also done some interesting shapes. So this is actually a mixer nozzle for an engine component, where you go from a circular shape to, people call it my flower pot, but it's actually got a technical reason. And so we can actually build, transition from shapes. These are small shapes. We can also build things. We can also build things the size of a bulkhead for an airplane. And so one of the first places that we're going to see this actually being an application is in very big parts, parts that are 13, 15 feet long. It starts with a 6,000-pound block of titanium. They machine it down to a 350-pound part. So all of that machining time, all of the chips and everything that are produced by starting from that big block of material and machining it down ends up being waste. And so what we're doing instead is we are starting with the base plate, and then we're building up the structure. And so instead of having to machine out all of these little pockets, we can just build it up and be much more efficient in the use of material. And feel free to thump these on the table. If they break, it's my fault, not yours. They are not breakable. They are not breakable. I have had these in schools. So, okay. So that hopefully gave you a feel for kind of why we're doing this and some of the interest in the process itself. Next, I'm going to talk a little bit about the process control. Right now, our process control is named Richard, and we're only as good as he can control everything that's happening in real time. And so hopefully I'm going to help you appreciate the value in being able to use modeling and simulation to help us in engineering to to make these processes more efficient and actually be able to run more cleanly. So these are some, not all, but these are some of the process variables that are involved with the process for making this actually work. And so you don't really need to understand what all these different variables are. Just keep in mind that the input variables, those are on the, is that my right or my left? On the left. The input variables on the left, those are things that we can control. So those are things that we're telling the machine, set your beam this way, move this fast, feed my wire this fast. Those are my control things that I can put new inputs into. The output variables on the right, these are, if I change something on that input side, the output variables on the left are some of the things that we see change. And so we'll see things like the temperature change, the size and shape of the melt pool, the geometry of the part that you're actually building. You also can see some distortion. If you look at some of the parts that are going around, particularly the tic-tac-toe board, that's actually an orthogrid stiffened panel, but it looks like a tic-tac-toe board. If you look on the back, you'll see a little bit of a depression where we've laid those beads down, and so that's caused by some of the residual stresses, and I'll explain that a little bit more later. But these are all things that we want to try to eliminate so that you end up with a good usable part at the end. So one of the first things that we wanted to understand is some of the cooling rate. The cooling rate controls the microstructure of the metal, which controls the mechanical properties. Your first layer is going down on a cold plate, and you've got a lot of area for that heat transfer to occur. As you build up, each layer is melting part of the previous layer, and you're building up higher and higher. So now my cooling path is restricted. Remember, I'm in a vacuum, so I have no conduction. Really don't have a lot of radiation, so my only cooling path, I don't have any convection. Sorry, I don't have convection. My only cooling path is really conduction, which is through this hot build and into this base plate. And so my cooling path is always changing, and that's changing the temperature. So that's going to change the resulting material, what I end up with at the end. This is something for us as materials engineers to understand. The next point is that it's a thermally transient problem. So it gets even worse. We really never hit steady state. And so all of you that do physics kind of stuff, you always try to shoot for that physics, that steady state. We don't hit steady state. We're constantly changing our temperature. So the picture on the top, both of the pictures here actually are showing some of the temperatures at a certain point. And so the temperature is going up and down as we put the next layers on. And so modeling is required, but it's really not easy to do. The next point is that besides that, remember that long list of input variables that I showed you on the left. Well, they each have a different impact on the output variables. And so if I change my wire feed rate, the top picture here is showing what happens when I increase the wire feed rate with constant beam power and constant translation speed. And basically I'll see that as I increase the wire feed rate, my bead width gets a little bit smaller and the height gets a lot higher. If I slow down or speed up how fast I'm moving the table, I have a similar effect but different. And so I have, as I speed up, I've got less material going in any one spot, so my build height is going to go down. And so trying to understand all of these interdependencies and how they impact my end result are some of the things that we're wrestling with. And in order to make the process so that we can get it out there into industry and to make it something that's really useful, you've got to be able to understand enough of these, either through modeling or through experiment, so that you can control the process. And so really that's what this slide is trying to say. If you look at the top picture here, you see a tall cylinder in the background and a short cylinder in the foreground. Both of them started, these are both built out of titanium, they both started with the exact same set of parameters. The short cylinder in the front was run with a constant set, so we didn't modify any of the parameters while we built. And so the heat built up higher and higher and higher, so it got fatter and shorter, and the whole thing starts kind of slumping over. As you try to increase so in order to control this, we were adjusting the temperature, we were adjusting some of the speeds and feed rates. And so the back of those two cylinders is showing what happens if you are able to actually control this. You can get a much higher build, much more regular bead width, and that's desirable because it's predictable. It's something that we know we can get the same thing time after time after time, which is going to be important for putting this into application. The bottom picture just shows some of the places where we have flaws. You can see kind of about a third of the way up there's a layer that doesn't look quite right, and so we had stopped for the night, came back the next day, everything was cold, and the wire didn't want to go down right, and so understanding all these sorts of things. Probably the biggest takeaway is that it's a challenge to be able to get it right, and then because we're NASA, we don't like to do things easy. One of the things that we're interested in is being able to take a process like this to space, to be able to build replacement parts, spare parts, to build large structures on orbit. And so now we don't even have gravity helping us. And that's really the key that I want you to for later on, I'm going to show you the impact that gravity has on this process. And then the last point here, just the number and the interdependency of the process variables really forces us to bring in some modeling simulation and try to turn the control over to the computer so that you're not as good as Richard is feeling on that particular day. And you don't have to try cloning Richard for setting up another operation somewhere else. Okay, so residual stress and distortion, we're going to talk next. Residual stress occurs because we've got a localized heat source. And so if you think about thermal expansion, if I've got just a little tiny pool where I'm melting, that one pool is trying to expand because it's getting hotter. It's being constrained by everything else around it. And so as we build, we're constantly changing the stress state. And the net result is that you get distortion. And what we find is that the plate will stay flat, but it bends. And so it's not a continuously curving plate. It folds right at the edge of where that deposit goes. So these are some of the finite element modeling analyses that we've done, just to give you a sense on some of the analyses, the modeling work that we have done. Trying to look at the stresses and how do the stresses vary as we continuously build up these parts. And so the first layer on, I'm bad with my rights and lefts. I guess it's the same up there as it is here, right? So on the far left, the first layer goes down, and you see that there are some fairly high tensile stresses on the very bottom. The pink is a tensile stress. The blue is a compressive stress. And so you get a compressive stress immediately underneath the deposit and a corresponding matching tensile stress on the back side of the plate. The thing that we found really interesting from doing this experiment is after a very few number of layers, you don't see a change in the stress state. And so the stress state is really built up during those first couple of layers that we build up. After that, things are hot enough and that they can relax and kind of relieve some of the stresses in the build, but that residual stress state is still built into the plate. And we've seen this crack 1-inch titanium plate. So these are not insignificant. They're scary stresses if you get it too hot. Something that really needs to be controlled in order to put it into practice. Again, this is another set.
Do you not have any control over the plate itself? You were talking about heating and cooling. Now you wish you had heat and you wish you could cool it.
So we have some control over it. So the question is, do we have control over the heat in the plate? And we do have a heated and cooled platen, so that we can put heat in to preheat it, and that helps a little bit. You can extract, you can cool it and try to extract the heat out. You can't cool it fast enough because of the point that I made earlier with the changing cooling path. And so there's only so much I can do to try to pull that heat out. One of the other things we've looked at is clamping arrangements. How can we clamp and hold it in place, what that does is your stresses tend to go up, but your distortion goes down. So if you're focused on distortion, that's one thing, but stresses are sneaky little guys that you really want to be careful of, because if you've got a lot of residual stresses and you load a part up like on an airplane, that stress acts on top of whatever load you put on that, and so you can start to induce cracks in a structure much earlier than you would expect if you've got high residual stresses. So you want to be real careful and make sure that your stresses don't get too high. Does that make sense? I can explain it later if you want. Basically, the point of this chart was just showing that depending on how far away we clamp from, what you're seeing is on the center line is the deposit. So this is kind of half of the deposit and one side of the base plate. And so we're just measuring how much the base plate deflects depending on how close we clamp it. And the closer that we clamp it, we get less deflection, but that means that we've actually plastically deformed the plate by forcing it to stay in place. So we get less distortion, maybe less residual stresses, but you've caused some changes to your material properties there. So all just things that as a materials person we're concerned about. This chart shows us the size of the melt pool. So looking straight down on the melt pool, and so the black is the first layer. It's a trace outlining the melt pool for the first layer. The reddish orange color is the second layer. The green is the third layer. The light blue is the fourth layer, and the magenta is the fifth layer. And so if we don't change any of our properties, we've measured how that melt pool gets larger with time. Now that we've got a measure for how things are changing, we can go in with some algorithms if we understand what the process interdependencies are. We can go in and be able to take those melt pools and try to force them all to look the same from one layer to the next. If we can keep the melt pool looking the same from one layer to the next, then we believe that our temperature conditions are continuous from one layer to the next, which will give us much more uniform properties and much more repeatable properties from one part to the next. Okay, I'm almost done with the boring stuff. Certification is the last of the boring topics. And really, this is just one chart. The picture there on the side is not real easy to see, and I apologize for that. But basically what it's showing is on the right, it's showing a base plate. On the left, so it's kind of standing the part up on its side. So on the right is the base plate, and on the left is the part that we built. And this is just showing the purple and the darker red color are showing specimens that we would cut from that. And the whole point is that you have to build samples. You have to build a lot of samples on different machines. You have to go back and try them. We do it one day in the summer, one day in the winter, to get the repeatability. So there's a lot of statistics. Any of you statistics teachers? There's a lot of statistics in certification. And so certification, we have S basis allowables, A basis allowables, B basis allowables. And what that means is an S basis is a very small data set. So we'll have maybe 30 specimens that we'll test for an S basis allowable. And so you've got the scatter associated with that. Standard deviations are kind of big. You don't understand what the tails of your standard deviation is looking like. To put something onto a flying airplane, you have to have A basis allowables, which is on the upwards of more than 1,000 tests. And so it requires a lot more rigors. There's a lot of requirements, on how many different places have to build the parts and how many different heats you have to use in order to try to get the statistics. That basically means if I test, so I do 1,000 tests and I build this database. So if I build a part to put onto this airplane and I do a test from that part that was built, I can say that yes, that should fall within the statistical database from this S basis allowable or from this A basis allowable. One of the challenges is this costs millions of dollars, and so it holds back the ability to put new technology new manufacturing processes or new materials into service. So we've been working closely with Lockheed Martin. Lockheed Martin is interested in this technology because they can save as much as $1,000 a pound on some titanium parts for their Joint Strike Fighter, the F-35 aircraft. They've invested on the order of $8 to $10 million to do the testing to certify this technology for one part on that airplane. And in the first production run, they can recoup all of that money and then some. It's big business, but the challenge is a lot of the additive manufacturing companies that are popping up are little companies. They don't have the multi-million dollars and the time to be able to invest in doing the statistics in doing everything experimentally. And so there are there's some processes out there that actually can do more rigorous statistical analysis on the data, so you can collect a much smaller data set, do more rigorous analysis, and be able to use some of the modeling to accelerate both in the time and reduce the cost in getting that certification. And so that's one of the things that we're interested in. We're working closely with some of the folks in industry and universities, because that can make or break adoption of new technology. All right. So this is where it gets a little bit more fun, a little bit more, visionary on some of the things that we want to do. So probably already talked about this, but these are real numbers. So we start with a block. The top line is showing a conventional machining process. We start with a block of material, machine away a lot of chips. So you've got the cooling fluids, you've got the chips, and you've got the amount of time. It takes you maybe 18 months to get that 3,000 pound block of titanium, and you're going to spend 6 weeks machining it down to a 150 pound part. And so the manufacturing that we're talking about doing, you can start with maybe 100 pounds of wire, 100 pounds of base plate that are all off-the-shelf items, so they're readily available. Machine a little bit, so you oversize it a little bit so you've got your finished machine parts, that are all within the tolerances that you're looking for. Same part on the end, but you've saved yourself months on waiting for that material, and also you've saved yourself a lot of time and energy in doing the machining and the building of that big block and transporting that big block around. So this is the reason that Lockheed bought into the technology. Boeing is interested, the Air Force is interested, the Navy is interested. So because they can save a lot of resources, and to them, resources, both time and material, is equal to money. So what they're talking about doing is, instead of building the entire part, you can maybe start with a simplified part. This is an engine casing that I'm showing here. And so start with a simplified preform, and instead of starting with something that's 3 inches thick and machining it down to leaf flanges and bosses and things like that, start with something that's maybe 1/4 of an inch thick, and then just add up the little bits and pieces. It reduces the billet size and what in the aircraft industry is called the buy-to-fly ratio. So how much material do you buy versus how much do you fly is the buy-to-fly ratio. As we start looking into applying this for future vehicles, right now the top picture shows how airplanes are built today. So this is a typical fuselage structure. It has a skin, and it's got ribs that are riveted onto it, stringers, what we call stringers, that are riveted onto it, and then it's got a ring frame up above that. So the ring frame goes in the circumferential direction around the fuselage to help with the hoop stresses. The stringers go parallel to the length of the fuselage. The fuselage is the place where everybody sits, along the length of the fuselage to give it stiffness. And the whole thing is riveted together. So it's thousands of parts. Aircraft industry is still very manual, and so these are all hand assembled. But they can take the right material for different components within that. And so if they want something that's higher strength or higher stiffness, because it's separate parts, you can put a high strength material for your ring frames, and a high stiffness material for your stiffeners, and a high toughness material so it doesn't crack. Good thing on a fuselage, for the skin. So one of the things that the EBF3 allows us to do is, because it's layer additive, we can build that same structure, but you've eliminated all the rivets, you've eliminated and you can still change your materials on the fly. So we've done some of that, changing the materials, so that I can still tailor the properties of my material to what the structure needs, but I can do it much more efficiently. And you know, the net result is I improve the performance and reduce the weight. One of the things that we're working right now with Virginia Tech and Lockheed Martin on is developing a design optimization tool. So this is all being developed in Nastran, and this tool is allowing them to design with curved stiffeners. And so because we can put the stiffeners wherever you want them, they don't necessarily need to be lined up on a nice straight grid pattern. And what can we do to design to improve the optimization of that design so that we can carry the load? One of the things that we've done is we've shown that you can carry the same load for less weight and actually change the acoustic resonance of that panel by changing the shape and location of those stiffeners. So a curved stiffener does not pass the acoustics. It doesn't ring the same as a straight stiffened panel. And so we've shown that we can reduce noise. What we're looking at doing now is tailoring the stiffness of the material along the wing, which helps us with flutter problems. Have you all seen the video of the Tacoma Narrows Bridge that sets up the oscillation, and in a couple of oscillations the whole thing ends up in the river? It's flutter, very common problem in aircraft wings, and it's a stiffness issue. And so if we can change the stiffness, we can try to eliminate flutter. Right now the way they do it, they add extra weight. There's one airplane that flew several years ago. They added 400 pounds of dead weight to help kill a resonant frequency. And so we're saying there's got to be a better way, because weight is fuel on an airplane. So these are some of the things that we're really interested in trying to do. Just a couple of pictures to showing you some of the more complex shapes. So the mixer nozzle concept I've already passed around here. We've built some airfoil that are wind tunnel model concepts. The picture on the bottom was actually an alignment tool that we built for a component that was going to be used on the last space shuttle flight. There was a system that broke on the outside of the space shuttle, and they needed to replace it. And so we were trying to get new technology into some of the EVA tools that are used. And so that was just we passed through the qualification tests. Because of the timing, we didn't get onto the last shuttle mission, but we were able to build something and show that it would have been equivalent, which is the first step to getting actually put into application. These are a couple parts that were built out of Ti-6-4, titanium 6, aluminum 4, vanadium. Again, just some different parts. That top one with the green background was built and tested on the F-22. Went through full certification testing. We've also built some wind tunnel models. The picture on the bottom is showing a fitting with some overhangs and flanges and things like that. And there's a number of different industries. Medical implants is a big one that's looking at being able to build custom hip implants. Aerospace, clearly. Tools and dies, sporting goods. And the remote location repairs is another area that we think has real potential. We're interested for doing some things in space, but it also has applicability for a number of different locations. Okay, now for the fun stuff. Supportability in space. One of the things that we did, so the first picture on the left shows our big system. It's 100,000 pounds, came in on 3 flatbeds. Obviously, it's not going anywhere. So we built the system in the center, and that one actually has flown on NASA's Vomit Comet, and I flew along with it, along with several other members on my team. And so I've got some videos to show you from that experience. We've also designed a concept to take to space. Are still waiting funding and the opportunity to be able to do so, but we've got some ideas on how we can make the system so that it weighs maybe 100 pounds, be able to take it onto the space station. So this is probably one of the things that I think that for middle and high school and even elementary school kids, this is a concept that may be able to apply for some of the things that you guys are interested in. This was our theory. Is that surface tension, you've got wetting forces trying to spread a bead out on the plate. And you've got surface tension that's trying to pull it together, and then you've got gravity that's pushing it down. And so our question was, how much is gravity helping us in this process? And how is that going to affect what we try to build in space versus things that we would build on Earth? Actually, some of these experiments helped us to understand the surface tension, which is now helping us to improve the process control on the ground. And so, even though this was for space, it's got real value here on the ground. So NASA has a C9. They've retired this plane. I think now that the last shuttle flight has landed, they've retired this plane, but they're also working with a company called Zero G Corporation that offers parabolic flights. They fly in parabolas, and during the nose down portion of the parabola, you end up getting 15 to 20 seconds of zero G. They can adjust the shape of that parabola to give you lunar gravity or Martian gravity. And what's that?
We're doing this on Friday, class here.
You're going to do that? Yeah. Actually, NASA does offer opportunities for student competitions. It's all paid for. The students are expected to put together, they have to put together a plan. If you want information, we can get you that information, because there are some student experiments that, and the students themselves will get to go and fly on this plane. So they design and build their experiment, and then they will give them a couple of flight days. So normally you fly, for us, we were flying 4 days in a week, and we got about 40 parabolas in a day, 15 to 20 seconds. So I've got about 3 hours in zero gravity in 15-second increments. That's a lot of parabolas. That was, over 1,000 parabolas that we over a 5-week period of time. And so what I'm going to show you now, this is looking in the window. So this is very similar to the video that I showed you earlier. This is obviously in our small system. We've got the system itself bolted to the floor of the aircraft. And this was a series of experiments. So the first 2 weeks, we had everything aligned just perfectly, and we didn't learn anything. This particular week, we had started too high off the substrate. And so again, what you're going to see is the beam. You can see the little kind of blue halo. Do you see that? In the middle of the screen, there's a little blue halo. That's where the molten, that's where the beam is. And so the beam is coming straight down from the top of the screen. And then you see the wire feed nozzle, and the wire is going to start feeding. And what you see is that the yellow blob is a molten pool. It's a molten pool of aluminum, but because we were too far away from the base plate, it didn't stick to the base plate. And so I want you to watch and see what happened. This was the first layer, and we learned so much from this, we let it go. And so I've got a whole series to show you here. So we're feeding wire. That ball is getting bigger. A little piece of the wire finally pushed through, and as soon as we got close enough to that base plate, the wetting forces pulled it down onto the plate. What we're building is a chevron, so just kind of a little 90-degree angle, and it's about 1.5 inches, maybe 2 inches on each of those two legs. And we traced over it, once going one direction and then coming back. And that's all we had time for in a zero-G parabola. After the zero-G parabola, of course, the plane is heading nose down into the ocean, and so they pull it back up from 25,000 feet back up to 35,000. So we get a 2G pull-out in between each of those segments. And so we stopped everything and turned it all off so that, you still want to go? So yeah, they stop everything and turn it off so that you can get back up to altitude to start for the next one. And so, upon contact with the plate, the wetting forces do overcome surface tension. Some people told us we were just going to build ball bearings. And so this is the next layer. Again, as we're a little too far away, you can see it pulling away. If you slow this down, you can probably make measurements on the shape of that molten ball at the end of the wire, and be able to do some measurements on contact angles and things like that to try to figure out exactly what your wetting forces are. So this is a couple layers later. So that was the first and second parabolas. This is layer 6. We didn't bother trying to fix it because we were going, wow, this is really cool. But what you see is as we get the height off. You can see as we come over the humps, you see watch the wire, and the wire is deflecting. This is 40 thousandths of an inch diameter wire. And so it's a fairly flexible piece of aluminum wire that we're feeding. And the errors become cumulative. So they get worse and worse. On the ground, it would just drip, very regular pattern, and you can recover from that. In 0G, there's nothing that shakes that drip loose from the end of the wire. And so it just keeps getting bigger until we make contact. And so this is the next layer. Okay, so this is our last layer for this particular. And so you can see when things go bad, they go really bad. But it's actually very, very interesting to watch. And so yeah, we only had planned on doing 8 layers, and so so the lesson learned is maintaining the correct height is critical for us. Maintaining the correct height is important for process control. But I think that in this one series of 8 15-second clips, we learned more about how the process is actually behaving and learned more about the molten pool dynamics with the difference between the surface tension, which is causing it to ball up on the end of the wire feeder, and the wetting forces, which is pulling it down onto the plate. We learned an awful lot just in this one sequence, and it took us a long time to get there. And it actually took us, so this is that serendipity pitch. If something goes wrong, you're going to learn more than if something goes right. And kids don't get that. But that's something that I firmly believe, because we didn't learn a whole lot. So this is just to prove, this was the next layer that we did. Watch the little ball at the end. Oh, it goes flying off. And later on during one of the deposits, you see it just kind of meandering across the screen. That ball is just floating around inside the chamber until we landed. But this is basically just to show what we did between when we moved over to build this next feature. This is a little circle. It's about the size of a $50. And we just went twice around, but we adjusted the height so that we were a little bit closer. And so basically what we were trying to show is that it does actually work if you get close enough. So don't want you to left with the thought that this just doesn't work in 0G. It does actually work in 0G, but we learned a lot about some of the physics in the part that didn't work. So why do we need this for space? We're talking about, so the space shuttle is showing the space shuttle docked to the International Space Station here. The space shuttle is no longer going to be taking supplies to the space station. So we are dependent on the Russian supplies and things like that. But we're looking beyond near Earth orbit. We're trying to look to asteroids and Mars and Moon and places beyond near Earth orbit. And so we can get to the space station in a couple of hours, and so we can resupply from there. But when you start talking about a mission to Mars, if you study your orbital mechanics, and so where is the Earth versus where is Mars, and how big are their orbits, it takes you about 8 months to get there, from here to there. And at the point where you get there is when you're kind of the closest between Earth and Mars. So Earth is moving away from Mars. You can spend either 2 weeks on Mars and then come back home for another 8-month journey, or you can spend 1.5 years on Mars, because at some point Earth is pulling away from Mars, and so Earth ends up on the opposite side of the sun. You can't get back. And so it really forces you to rethink the way you design the mission. Those astronauts that go to Mars are going to have to be completely autonomous, which means that they need a Star Trek replicator that can build them whatever they need, because they can't predict what's going to fail. That's been proven. And so so that's one of the things that we're filling that need, is that we're offering them a tool that can be used to build other tools. Just like Christopher Columbus, he didn't come bringing the entire everything to build a house, right? He brought a bucket of nails, he brought a hammer and an anvil. He found ore, and he made what he needed based on natural resources. And so it's the same concept that we're trying to pitch to NASA. If we're going to go and set up any sort of operation, I'm not going to go so far as to call it a colony, but to set up any sort of operation on another facility or on another being and have long-term longevity there, you're going to have to be able to support what you bring along. And so this is one of the tools that we've proposed they may need to do that. We're looking at, can you build it handheld so that you can go in and use it like a hot glue gun, only it's structural metal, to be able to replace something that might fail, or be able to set it up as you've seen here where it's more automated. The nice thing about the automation is you can actually ship the files from the Earth, so you can run the thing completely remote. And so you could send the machine up, and as long as there's material for it to be able to work with, you've got something that you can work with. Concept for building very large space structures. Now you can send up big spools of wire and be able to build stuff bigger than the equipment itself using Tinker Toy type methodology for space-based assembly. You could use this to weld and build joints and be able to build very, very large space structures more efficiently and more quickly than you might be able to with an assembly. So you're not limited by the size of a single payload that you can send up into orbit. We found that in talking to the military, talking to the scientific bases, this is a picture of McMurdo Station down on the South Pole. McMurdo spends 80% of their time in the winter. Of course, you can't go outside because it's nothing to see and it's kind of cold. But they spend 80% of their time on maintenance. And so this gives them something. When resupply only comes every 6 months, it gives them a way of having that self-supportability and sustainability that they don't necessarily have. The Navy ships are interested, as are so the aircraft carriers as well as submarines are interested in being able to build replacement parts to do repairs closer to the theater. The Army has actually built what they call a mobile parts hospital. And so it's not for body parts, it's for Humvee parts. Everybody goes, it's a hospital. But it's for Humvee parts and that. But they have sent a couple of units to Afghanistan and Iraq and have been building replacement parts. And what they found from that was that they went thinking that they were going to be making like tie rod iron parts. Thank you. parts for Humvees, right? And so what they found was that the soldiers would come and say, hey, can you build me this jig? I've got to hang out my Humvee holding onto my machine gun. Can you build me a jig that can hold it in place? And so the ability to build something opens up build whatever you need, where you need it, opens up the possibilities for other applications. And so, from a CAD drawing standpoint, that's exciting. Because if you can, it's kind of if you can draw it, we can build it, except for MC Escher. But if you can draw it, you can build it. And so it's something that it captures the imagination, and I think that it's really important that, because our current designers don't get it. The next generation is the generation that's going to need this kind of technology, and they're the ones that are going to really make this technology something that's ending up being used. So this is just kind of our vision. We've done ground testing. We're trying to do some certification testing for, number 2 is certification testing for putting it into use on airplanes. 3 is the Vomit Comet experiments that we did. We'd like to take it to space station as a test bed for further long duration missions, but ends up circling back that ability to show that you can be autonomous for the astronauts also gives you autonomy back home. So hopefully I've covered all these points. If not, we can talk later. But there's a lot of opportunity for modeling and simulation in advanced manufacturing, things like electron beam processing. There's thermal modeling, there's process modeling, there's residual stress modeling, which is more your mechanics type of modeling. There's statistical analysis that's required for certification. There's structural design, so finite element and more CAD type drawing. And then, some more your physics kind of experiments with surface tension, wetting forces, and things like that. And we have, our portable system was built primarily by college students. I usually have a cadre of students every summer following me around, and the group that, and this is not just me. I've got a big group that's working, and I need to acknowledge them because they've really been the reason that we've been so successful. But if you've got some ideas on things, some experiments, or gee, can you build this or something like that, we're talking about trying to do some design competitions with students, and hey, if you can design something, maybe we'll build the winner's concept. Show something that's useful, and so we're very much interested in trying to get this into the hands of the students. And so part of the way I see that is to be making it available for the students. And so so my offer to you, and as well as the folks that are online, that are remote from here, is if you've got some ideas, if there's some experiments that we can run that would help you to be able to take this into the classroom, let me know, because we'd be happy to do some things like that to be able to help you. So that's what I have, and at this point I've got a few minutes for questioning. I'm sorry we got a little bit long. We got started late. So, questions?
How is this different than just a MIG welder? I mean, not just how is it different, but why would I want to invest all that rather than just current welding technology?
Okay, so that's a good question. How is this different from MIG welders, and why would we want to invest in electron beam technology rather than a MIG or so the electron beam is a little bit cleaner than MIG. For your purposes in teaching students and for building basic stuff in classrooms and that, a MIG welding system is a great alternative, because this is a multi-million-dollar. This isn't something that you're going to put in your lab. A MIG welding system you can invest in a couple of $1,000s and be able to do a similar. So the control piece and the how do you introduce the wire into the welder and then control to build up. That's very similar as you go from a laser to a MIG to an electron beam gun. The reason that we chose electron beams over lasers or arc welding is that it's cleaner, it's got a lot more control, a little bit more efficient. It's a lot more efficient in power than a laser-based system, because it's basically an electrical process. So so that's the reason that we've gone with it. But there are corollaries that would work very well and enable you to have a similar type of capability for a lot less money.
I have a question. How you were talking about you get residual stresses near the base. Is the solution could be that you heat treat it afterwards to make it go away? Is that
So the question here is the residual stresses that build up in the base is one of the solutions to heat treat it, and that's exactly what they're doing right now, is taking it, do either an intermediate stress relief, so build partially, take it out of the chamber and put it into a furnace to stress relieve it. That's the way we would stress relieve welding stresses, or even machining stresses. So there are residual stresses in everything, and so that's a very common practice. We're looking at, can you balance? So one of the approaches is, can I balance my residual stresses? If I put the plate in the middle and I build on both sides, I can maybe balance those stresses, and so that's another approach that's being taken. But yes, you can use heat treatment. That's the first line of business. The first line for ground-based manufacturing would be to take this part afterwards and do a final heat treatment to get the right properties and to stress relieve it. If you're going someplace in space, you don't want to have to bring that furnace with you. And so, longer term, if there are things that we can do while we're building it to prevent them from building up in the first place, that's where we want to go. But certainly that's a good approach for enabling this to get into the market today. Other questions? Anybody from the remote sites?
You don't want to take your milling.
Thank you.
You don't want to take your milling machines with you either. So is there a drive as well to get this to be popped out, plug it in, done?
Yes, yes. So you know, the question is, you don't want to bring milling machines with you either. Is there a drive to build net shape? And yes, that is what we're doing. That is one of the things that we are very interested in doing, is can we build this net shape? The power of the electron beam is you can use it to drill holes. You can use it to reshape the surface. If you look at the little wall, the flat L-shaped piece that went around, if you look on the side where the base plate's been cut off, you can see that the surface finish is different on that side than the other side. What we did was we used the beam to try to eliminate the evidence of the layers, so try to smooth it out. We've also looked at the concept, just like milling machines have tool change capabilities. We've looked at, you know, can we design our system so that the E-beam deposition head is one tool and it actually has like a little Dremel. You don't need to do a lot of heavy-duty machining, but if you need to cut teeth or cut threads into a screw or a hole, can you do something like that? And so that's very much in the interest to be able to build final shape parts, because you're right, you don't want to have to bring a whole milling machine. I think that you can do an awful lot with a little versatile tool like a Dremel that would have value for other things anyway. And because the last thing that I want is for the one and only repair tool to break. You've got to have a way to be able to fix your tool. And so I'm a real proponent of, you bring along maybe another little hand tool, you combine the two as needed, but then you've got a way for fixing and repairing each other so that you are not dead in the water if something goes wrong.
Sorry.
Go ahead.
I know when you're wire welding, you know, the wire will get kind of jammed up every now and then. This being offside and you're running it by computer programming, does it have its own method of cleaning, or is the precision just so much more accurate that it doesn't happen?
So the question is, wire welding, oftentimes you can get, you know, snags and you know, wire buildup or snags in the wire feed lines, and what are we using to try to eliminate that. And so one of the things is precision, and we've designed some supports that help to guide that wire all the way so that there's not as much opportunity for it to create a little bird's nest in there. The right wire helps as well. If you go to too small a diameter wire, it can cause problems sometimes. So there's not a that is an area that still needs some development. We've got some workarounds that have worked very well. So we haven't had any wire snares in the Vomit Comet experiments, because once we buttoned that up, we did all 40 parabolas, and if something went wrong, we were just done for the day, and we had to ride out the other parabolas. and then what do we do? Actually, what we did, and so on your thumb drive is another set of experiments that we ran when we were doing these experiments. I brought along, so I talked to Sharon Bowers, who is one of our educators that worked with us at NASA, you know, here at Langley back in 2006. And so she talked me into bringing along a pendulum, some clackers. It kind of shows Newton's laws of motion, where you've got, you know, for every action there's an equal and opposite reaction. I brought some magnets, and I brought this little, it's an offset cam on legs so that it kind of hops around. And so we did a series of experiments in 0G, lunar gravity, and actually during the pullouts in high gravity, and looked at the periodicity of the pendulum and how quickly the clackers reacted, you know, what kind of reactions did you get from the clackers and things like that. And so that video is also on your disk. And so if that is of use, you know, if you want to look at what does gravity do to the laws of motion, that is also already there for you on that disk. So.
One more.
So what is the next big challenge for you? What area are you trying to improve on in technology?
So the question is, what's the next big challenge of the area we're trying to improve on? Like we haven't had enough already. Actually, modeling and simulation is one of the next big challenges that we are really working hard. We'd like to be able to build a simulator of this process so that other people can do virtual experiments without having to have the multi-million-dollar hardware to be able to do the experiments in real. So the modeling and simulation is one area. We are almost finished with a closed-loop control to turn the control over to the computer. And what we want to do next is applying it. Some of the things that I was showing with the stiffeners, where we can change the chemistry. We've got a multiple wire feeder, so we can change the chemistry from one wire to the next by feeding two wires at the same time at different speeds. And so being able to do graded structures where I can put kind of any material with any kind of microstructure you might want at different points to try to improve the performance of the structure. Those are things, as well as if we ever get the money to build a small system to send into space. That's the other thing that we'd like. So we've got kind of the aeronautics thrust. A lot of our funding has been from the aeronautics programs at NASA. And so the aeronautics thrust is improving the performance, reducing the fuel burn for commercial transports, and that we're looking at through the curved stiffeners with the functional gradients, trying to improve the performance of those structures. And then being able to push the thrust for building replacement parts like space station is the other thrust. Very good. Thank you. And I think that my contact information is on here, but if you've got any questions, I'd be happy to answer them after the fact if you want to send me emails or whatever, and I can give that to you. Thank you very much.
Thank you.